made. Primary mirror, 18 times repeated. Secondary mirror, that's now also gold coated. Tertiary mirror, fine steering mirrors, lots of mirrors to get all the light in focus. By the way, we don't use gold to coat our mirrors because the project has so much money. There's only 2 grams of gold in the entire telescope, which is about $2,500 by today's market prices. But we use gold because it's so highly reflective in the infrared. We use silver or aluminum on telescopes like Hubble because it lets you look further down in the blue or even the ultraviolet. We use gold to look all the way in the infrared. You get this much better throughput, right? It's the way to do it, to build an infrared telescope. And then there's all these support structures and the backplane structure here, the various support bars. I'll show you in a minute, the sun shield, the spacecraft electronics. Everything is coming together. As of today, well, a few months ago, 97%, it's probably more now, but close to 100% of the mass is designed and built, and more than 60% has been weighed. Here's the first 6 out of 18 mirrors, gold coated and ready to go. They're in the chamber here in Marshall Space Flight Center in Alabama to get tested for cracks and see the hexapods and all the cabling in the back works. And this is how that's being done. So here's the mirrors as delivered. The total spec is that they all be better than this number, and most of them show numbers that are smaller than that, with 2 exceptions. These mirrors are a little less good, but the overall performance has to be better than 25 nanometers, which is basically the surface accuracy, the roughness of the asphalt on the freeway, so to speak, or the roughness of the beryllium on the mirror after the gold coating gets on. And in almost all cases, that is like this or better. In this case, it's a little worse. See how we're doing with time here, Gary? Yeah? Okay, we'll only have one time for a little anecdote. Most of you are too young to remember. 5 more minutes? Okay. So then I'll say this. The Hubble Space Telescope mirror was the most precise ultraviolet mirror ever made to precisely the wrong figure by mistake. Unfortunately, a shuttle astronauts fixed that. They put corrective optics in, but it was just polished to the wrong shape. These mirrors, they get polished at room temperature, the only way you can do it. So these are the most precise infrared mirrors ever made. Listen carefully. Made by mistake to exactly the wrong figure at room temperature. So when you bring them down to 40 kelvins, they have exactly the right shape. Right? And so it is a very tiny difference for beryllium between room temperature and 40 Kelvin that you need to polish out. And that's also being done. That has been tested. All these mirrors being brought down to 40 Kelvin. That's where they're all at. They're all ready to go now. They're being mounted in the telescope. Here's the telescope viewed from the top. Here's the support part of the secondary. I don't show this in a movie, but this all works. It folds open automatically, repeatedly as many times as you want. Here's the telescope truss. I'll skip that one for the sake of it. Here's the sun shield. A few months ago, completely rolled out and automatically deployed with people standing by the side, a couple of guys in the little hall just to make sure everything worked. Nobody intervened manually, but you know, if something got stuck, they could have. In space, of course, you can't bring somebody in there, so everybody or everything needs to work properly, automatically. This was an engineering model. This was not yet a flight model, so now they have to do the same thing for the flight model, but there's good hopes that they will get all that done. For the sake of time, I'll skip over the instruments that the Europeans, the Canadians, and us have built. Just to say there's at least 27 US states. I hope in the future also Kentucky will get involved in building future generation of instruments. 10 European nations and Canada involved. So it's a very robust project robotically and politically. We're now in the process of testing it all in a small chamber to make sure all the instruments work. That happened last summer and this summer. We put all the instruments in this chamber, cable them up, make them talk to what we call IRAF for the astronomers. It's basically a data taking program. And of course we close the tank, pump it down after we take the technicians out and bring it down to 40 Kelvin. And it has been done twice and it worked just fine. And so now we're in the process of putting it all together, all the assembly parts of the big Lego puzzle, and then test the entire thing, which everything has to work 100% correctly, in the largest thermal vacuum chamber in the world. This is in Johnson Space Flight Center. The chamber is over 50 years old. It was built first for the Apollo program. That was not the entire Saturn V, but it was the entire moon lander and Apollo capsule that sat in here, and they were vacuum testing it. This is the largest door in the world, about 20 meters, or I forgot how many feet, at least 60 feet or so. So the entire telescope gets rolled in there, and they close the door, pump it down 40 kelvins, and then make sure that it focuses, and all the hexapods, all the focusing mechanisms, everything works. So how do you observe first light with that? In the last couple of slides then, I'll show you how complex that is. The first stars, like these cosmic fraternity members, but even more massive, maybe about 100 solar masses, in the very early days, so we're now talking about when the universe was 10 or 30 times smaller than today, talking about the first few 100 million years, they formed very quickly, and they formed these other stars like the sun, or a little more massive surrounding them. And they consist out of all these little pockets of these small galaxies that over the course of time, mini galaxies, dwarf galaxies as we call them, would have started merging very quickly and form bigger galaxies like we see today, like these ellipticals and spirals that I showed you. I'll skip that for the sake of time. I will show you what these images look like. This is a false color image. This is what the deepest image of Hubble looks like today. Almost 600 hours of integration time, or 841 orbits. Again, it reaches this one firefly from the moon type faintness. Now, I don't show any real color here, just the color indicates brightness. And all these faint little dots are faint galaxies, very far away. And there's so many of them, it's almost like you can not see the forest for the trees anymore. About 45% of the entire image is filled with object pixels, so we get really crowded here. If you display that in color, it looks like this. This is more or less true infrared colors, and all these little circles indicate the galaxies that are seen in redshift 7 or 8. That's about the first 700 or 800 million years after the beginning. These little yellow circles indicate the more rare galaxies seen even further back, the first 600 million years, or redshift 9. And then here's one. It's hard to see, but you can see it in the original data here in the red circle at a redshift of 10 or 11. A little smudge there. It's only seen in the reddest of all filters. And that is what one of these first galaxies will look like. Find a very tiny smudge, all the light shifted from the ultraviolet where the stars are formed to the infrared. This is the rendering you used to see the Hubble Ultra Deep Field, where blue is blue and red is red. Where we now emphasize the blue colors, but this is more the kind that James Webb will see. So how do we take it from here? So what we're going to find, I'll skip over this one technical chart for the sake of time. What we're going to find is these very rare objects, these first light objects with the first stars surrounding by the second generation of stars, that are going to be very rare. The Hubble Ultra Deep Field has kind of already shown that our numbers are diminishingly small by the time you go to the larger distances and the higher redshifts. And we now think that we have to do the following. In order to see many of them, the universe is a little perverse in the sense that these things are so faint and so rare that you have to integrate with, even with James Webb for hundreds of hours, and do a fairly large swath of sky to see a number of them. That we're actually going to use the foreground objects like the galaxies in a cluster or a group in the foreground, and use the gravitational lensing to magnify the background galaxies. So here you see a couple of galaxies look really weird. They're like gravitationally magnified. And that's because, you know, some of the very distant galaxies in the background are so rare to see that I wouldn't see them unless they come to us via foreground, and then the gravity in the foreground magnifies the light, and we see it come from two different or more than two different directions. And we can see it better. Here you can see a better version of that. Here's a massive cluster. And these arcs here are galaxies in the background that have been magnified by the gravity, basically Einstein's theory of general relativity, that light comes to us on the various directions, and we see it magnified in arcs. And we think we have to do this a lot with James Webb. In fact, we may have to do this exclusively with James Webb for the following two reasons. And this is my last chart. That A, the fainter we go, the more the sky will look like the forest where you can't see the trees, because there's so many galaxies that the background forest will be hard to disentangle. And secondly, not only is the forest very dense, but secondly, some of the trees, the same tree may appear more than once because of the gravitational lensing, like this guy here in the House of, you call it House of Mirrors, or Fun Mirrors on the State Fair. And so we think that both effects are going to be relevant for the James Webb Space Telescope. First of all, the image is going to be very deep and very packed, and secondly, we have to use this gravitational lensing to see these rather rare first light objects that were born in the first few hundred million years. So I'll give you my conclusions, most of which I have already said. You know, the Hubble sequence, the one that Hubble, our Louisville citizen, discovered over, well, about 100 years ago. And the Hubble telescope set the stage for all this to measure it far more precisely in the last 20-some years. And then the Webb telescope project is now on time. There's no technical showstoppers. It had some hiccups and overruns in 2011, but more than 97% of the stuff is built, and we're now integrating and testing it. And this telescope should be great to do everything from the Earth-like exoplanets around nearby stars to the first stars and star clusters in the first 200 million years or so, and find the galaxies that basically kept the universe alive and ionized ever since then. So last but not least, I want to invite the younger generation to be part of this, become students to work on this project, either here in Arizona or other places, and help us think about what should come after the Webb telescope, perhaps telescopes that explore the dark ages or do other things. So I'll leave it at that, and thank you very much for your time. Shoot, otherwise you can use mine.
You're back on. Oh, okay. Push the bottom for 3 seconds.